In this section, we're going to study some alternate coordinate systems that we can use when we need to graph points and graph surfaces and things like that in 3 dimensions. And as a starting point, let's go with something that you've already studied in the past, which is polar coordinates. So in 2 dimensions, we know that instead of identifying a point by its x and its y value, we could instead identify it by how far it is away from the origin, so r, and what angle it makes with the x-axis, right? And so we have this picture here. And then using trigonometry, what we know is that the relationship between these 2 coordinate systems is that the x is always r times the cosine of theta, just from right triangle trigonometry. The y is r times the sine of theta. But then we also know that x squared plus y squared gives us r squared. And the tangent of theta is the opposite over the adjacent, so y over x. So that's polar coordinates. So when we talk about cylindrical coordinates, that is just the 3-dimensional version of polar coordinates. Okay. Now, we call them cylindrical coordinates because when we talk about polar, we're kind of talking about, okay, identifying things by its location on a circle, right? What's the radius of the circle and what angle are you at on that circle? So that's where the polar is coming from. So then cylindrical, a cylinder is just a circle that has a height, right? So all we're going to do for cylindrical coordinates then is give our polar coordinates a height or a z value. So what we're going to do is we're going to identify points by r theta, just like with polar, but then a z for the z. So it's literally just doing the polar coordinates in the xy plane and then going up however far in the z we need to go, or I suppose down however far in the z that we need to go. So the nice thing is if you already know your conversion equations for polar coordinates, it's the same for cylindrical coordinates because there's no conversion to do between the z value. All right, so let's kind of get a sense of how we would do this. So this is written in cylindrical coordinates. So let's remember that this is our r, this is our theta, and this is our z. All right, so first of all, if theta is 3 pi over 4, let's think about where that's at. That would put me, and I should probably make some tick marks here before I get going too far into it. So make some tick marks. And here we go. And then I better also make them in the z as well. All right, so first of all, we want to go an angle of 3 pi over 4. Well, remember that if we're just talking about the xy plane, 3 pi over 4 is over here. So it's in quadrant 2. So as I make 3 pi over 4, I'm going to go at this angle here so that I'm in this quadrant of the xy plane. And I've got an r value of 2, so that's going to, take me out maybe like right there. But then I'm going to go up 5. So, and right now you can see by the perspective I'm at that I'm about right here. So I'm going to go up 1, 2, 3, 4, 5. So I'm going to put the point right there. So this has a length of 2, and that has a length of 5. Okay, and that's my point. Now it also asks us to convert those into rectangular coordinates. Okay, well I know that x is equal to r cosine theta. So for us, that's 2 cosine of 3 pi over 4. And the cosine of 3 pi over 4 is negative root 2 over 2, remembering our trig, which is negative root 2. And then we can do the same for y. Y is equal to r sine theta. So y is 2 times the sine 3 pi over 4, which is 2 times the positive square root of 2 over 2, which is square root of 2. So this is going to be an x value of negative root 2, a y value of positive root 2, and then a z value of 5 still, right? Because that remains unchanged between the coordinate systems. And just as a note here to kind of check our accuracy, square root of 2 is about 1.41. So does it look accurate to say that I go negative 1.41 in the x, positive 1.41 in the y, and then up 5? Yep, that lands me in exactly the same place. All right, so let's look at example 2. It wants us to find the cylindrical coordinates of the point indicated here that has these rectangular coordinates. Okay, so this here is my x. Get my different color here. This is my x. That's my y, and that's my z. Okay, so what do we know? We know that r squared is equal to x squared plus y squared. So that means r squared is negative 3 roots of 3 squared plus 3 squared, which is 9 times 3 plus 9, which is equal to 36. So r is equal to 6. And then remember, theta we're going to find by taking the tangent of theta is equal to 3 over negative 3 roots of 3, which means the tangent of theta, to simplify, is 1 over negative square root of 3. And that should, look familiar in terms of special values on the unit circle. That's 1/2 divided by negative square root of 3 over 2. And so what we should note here is what quadrant this is in, right? If the y is positive and the x is negative, this means we're in quadrant 2. So where in quadrant 2 is the sine equal to 1/2 and the cosine equal to negative root 3 over 2? That's going to happen right here at 5 pi over 6. Okay. Now, if this didn't happen to be special values on our unit circle, then you would just use the tan inverse. And if the tan inverse gave you something in the wrong quadrant, you would just add pi to it, or in order to get what your theta is. But we now know that theta for us is 5 pi over 6. All right, so moving on to the next page. I don't even think I meant to make a second page of this, but just accidentally did it. Now we can kind of summarize what we've got here. So we've got polar as 6, 5 pi over 6, negative 5. And then our rectangular, negative 3 roots of 3, square root of 3, and negative 5. And this is about negative 5.2. This is about 1.7. So what we can do here is we can graph both the polar and the rectangular and see if they're matching up with each other. So let's put some notches on our axes here. Okay, so x needs some as well. Let's start with the rectangular this time. So we're supposed to go negative 5.2. So 1, 2, 3, 4, 5.2 abouts. And then about 1.7 in the y. So 1.7 in the y, you know, parallel to the x-axis puts me right about there. And then we're supposed to go down 5 from there. So right now it's lining up just above 2, so this should line up just above negative 3 when I go straight down in terms of the perspective I'm looking from. So we should get right about there. So you go that far in your x, there in your y, and then there in your z. So negative 5.2, 1.7, negative 5. Okay, so now let's try it with polar. So we're saying we should go at an angle of 5 pi over 6. So that's almost all the way over here, right? So that's going to make this angle. And then it should be a length of about 6. Okay, that seems like that would be a length of about 6 if I went and connected it up here. And then I could send it straight down negative 5. And so I get the same thing when I approach that in terms of the cylindrical coordinates. You have to forgive me if I kind of screwed up there. I'm so used to talking about polar, right? Because it literally is just polar with a z value attached, but let's use the proper language here. Cylindrical coordinates. All right. So now let's talk about actually making some graphs. So what it wants us to do here is sketch the graph of the function whose equation in cylindrical coordinates is z equals theta. Okay, so z equals theta. So what that, here's another one of those situations where we have a formula and one of the variable types is missing. There's no r. No r, though, means that z equals theta for all r. So it doesn't matter what r is. Now, we know then that means that we have this infinite, that all r values exist, but that'd be really hard to graph. So we will stop it at some point. So here's what we're going to do. For z equals theta, let's go ahead and just make a table, right? So when theta equals 0, that means z is 0. So theta being 0 is when you're along the x-axis. So I'm just going to draw a line right here. I'm going to go ahead and stop it right there, though. Okay. Now, what about when theta is equal to pi over 2? Well, then z equals pi over 2. So no matter what r's we're talking about, if we go up pi over 2, then z is going to be pi over 2, when theta is pi over 2, z is pi over 2. And we know theta is pi over 2 when we're along the y-axis. So I'm going to parallel the y-axis here. Okay. What about when theta is equal to pi? Well, then z equals pi. So then if I go up to pi, okay, well, where's pi? Pi's over here on the negative x-axis, and so I'm going to parallel there. Okay. And then 3 pi over 2, it would be at 3 pi over 2. So I go up 3 pi over 2, and that's when you're pointing down the negative y-axis. So I'm going to put another line like this. Okay, but then of course what's happening here, I know that these really extend out forever, but to give myself a sense for what's actually occurring here, I made this a little bit too long, so let me shorten that up. I'm actually getting something like this. Okay, I'll clean up my mess over here. All right, so what is this? Well, if I kind of maybe do some shading here of some sort, see if I can make this look a little bit better. What I have is I notice that the level gets higher and higher as I go. So you know what this is kind of like? This is like the ramp in a parking garage. Okay. And I can go ahead and, if I want, use, oops, I forgot to get it ready. This won't take long. Use our 3D grapher. And so there's all these options, and so what you can do is you can select z as a function of r and theta. So if I select that one, then I can just type in theta. And I do that just by typing the word theta in, and look, there it is, right? There's our parking garage that's climbing and climbing and climbing as I go. So kind of a cool example there. All right, now let's look toward the bottom of this page. So let's find the equation in cylindrical coordinates for the equation x plus y plus z equals 1. So we know that x plus y plus z equals 1 is just a plane, right? So, so we know that that's pretty simple in rectangular coordinates, but what would it look like in cylindrical coordinates? All right, well, I think what would make sense is, as you saw in that grapher we just looked at, it's nice to get z as a function of r and theta. So a first step might be to solve for z here. So x plus y plus z equals 1. Let's just move those over to the other side. So 1 minus x minus y. And so then we get z is equal to 1 minus r cosine theta minus r sine theta. Okay, and that's all there really is to it there. If I go and I type that in to our grapher, hopefully what we'll see is a plane. So let's try that. 1 minus r cosine theta minus r sine theta. Now at first you might kind of look at this funny, but it is a plane. It's completely flat. It's just making the circular disk here because of the values that it's choosing to graph, because I'm giving it instructions to graph from r equals 0 to 5 and theta equals 0 to 2 pi. So when you're graphing according to r values, of course it's going to make a circular boundary as you go. And of course the only reason it's kind of flat on part of those edges is because of my discretization. If I go like 100 here, then you really see that disk forming. But that's completely arbitrary. We know in reality that plane extends off infinitely far in all directions. So that's cylindrical coordinates. Okay. Now we're going to talk about another one called spherical coordinates. So if cylindrical coordinates, if the idea of those is that, you know, you're kind of finding points on a particular cylinder. So you're finding points according to saying, what's the radius of my cylinder, at what angle am I at on my cylinder, and what height am I at on my cylinder. This type is called spherical coordinates because we're saying, let's find points by creating a sphere, and we're going to look at its radius. But then we're going to look at two other things. Theta, the angle it makes in the xy plane, that's the same theta as in our cylindrical coordinates and our polar coordinates. And then phi, which is this angle that you make with the z-axis. Okay, so this is how you're identifying points. Rho, that's the distance from the origin. Okay, that's the Greek letter rho. Theta, phi. Right, so you tell me how far out to go. You tell me what angle to make here with the z-axis, and then you tell me what angle theta in the xy to go to. That's spherical coordinates. So what I want to do is, instead of just giving you the way to convert between rectangular coordinates and spherical coordinates, I want you to try to figure out for yourself how to express this in rectangular coordinates, this point right down here. Okay, so this is already in spherical, so you know that this is your rho, this is your theta, and this is your phi. And I want you to see if you can use trig in order to figure out what the x, y, and z of each of those are. So pause the video, give this a try yourself, and then you'll see my solution when you come back. All right, so how do we attack this? Well, I would just refer to this picture. Okay, so we need to know what the x, y, and z are. So here's maybe first of all, here's our z. Maybe we should start with that. So our z is this height here. But when I draw a line from my z out here to the point, I form a triangle. And it's a triangle that's created that has a hypotenuse equal to rho, and it has this angle here equal to phi. Okay, now in my problem, I know that phi is equal to pi over 4, not 3, pi over 4. And I know my rho is equal to 3. And for that matter, I know theta is equal to pi over 3. So I can actually work with actual numbers here. Okay, so what would I do with this? Well, since I'm forming this triangle, and it is a 90-degree angle here, it's a right triangle, I know that trig tells me the relationship between z, which is this, right? This z, and the other sides and angles. So I know that the cosine of phi has to equal the adjacent, which is my z value, over my hypotenuse, which is rho. Okay? But I can put actual numbers in here. So this would be the cosine of pi over 4 is equal to z divided by 3. So multiply by 3, multiply by 3. So I end up with 3 cosine pi over 4 is equal to my z. But I know that the cosine of pi over 4 is root 2 over 2, so there's my z value. So see, I just used right triangle trigonometry to figure that out. All right, so now let's take a look at the x and the y. Okay, so let's start off with the x. So the x, of course, is right here, and we're extending this out. Okay, and we're making another right triangle, and we know this angle here. So here's my x, and here's my y. All right, so on the one hand, I know that the x value has the relationship as if I take x over the hypotenuse, right, which is r, right, and I'm calling it little r because that's the distance from the origin just in the xy plane, right? So that's just from polar coordinates or from cylindrical coordinates. So x over r is equal to the cosine of theta, right? But I know the cosine of theta. The cosine of theta is, well, excuse me, theta is pi over 3, and so I can figure out the cosine of pi over 3 is equal to x over r. Okay, do I know r? Well, that's a good question. Let's go back up to the picture. If we look carefully, r and rho are both sides of a different triangle. So I could note that this is a little right triangle right here. Okay? And I know that if this angle right here is phi equals pi over 4, then also geometrically this has to be phi equals pi over 4. So what that tells me is that the sine of phi, or the sine of pi over 4, has to equal r, the opposite, over rho, the hypotenuse. But I again know sine of pi over 4, oops. So the sine of pi over 4 is equal to 3 over r, or excuse me, r over 3. So that means 3 times the sine of pi over 4 is equal to my r, which then allows me, instead of r, I can stick this in for r down here. So this will be 3 sine pi over 4. So I can multiply both sides and get 3 sine pi over 4 times the cosine of pi over 3 is my x, which is 3. The sine of 3 pi over 4 is, pi over 4 is root 2 over 2. The cosine of pi over 3 is a half, so that's going to be 3 square roots of 2 over 4 is my x. And then luckily my y is very similar. Y, though, is going to relate to theta by saying the sine of theta equals y over r. Okay, but then we know that the sine of pi over 3 is equal to y over, it's the same r as last time, 3 sine pi over 4. So our y value is 3 sine pi over 4 sine pi over 3. That's our y value, which is 3 root 2 over 2, root 3 over 2. So this is going to be 3 square roots of 6 over 4 is equal to my y. So that's a lot of work we just did to figure out this x, y, and z. Okay, but here's what it also did. It also gave us the blueprint for how to do this with a lot less work next time. Because if I look here, in each of these, and I want us to focus in on this one, and this one. In all of them, rho, which is 3, came first. Then we had the cosine of pi over 4, the sine of pi over 4, the sine of pi over 4. That's your phi. And then in these two, in this one I took cosine of theta, and this one I took sine of theta. So that leads us to the next page, which gives us the general formula for spherical coordinates. So x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is always equal to rho cosine phi. And then lastly, because rho is the radius of a sphere, it makes sense that you take the x squared plus the y squared plus the z squared in order to make rho squared. All right, so now let's do a conversion that's going to be a little bit faster. We're going to say we've got the this point is given in rectangular coordinates, so let's find the spherical coordinates of this point. So x, y, z. So we can find rho real fast, right? Rho is just 2 squared plus negative 2 square roots of 3 squared plus 3 squared, which is equal to 4 plus 4 times 3 plus 9 is 25. So rho equals 5. So that's fairly painless. Okay. Now let's look up at these other formulas we have to work with. Well, now that I know rho, I also know that I have z, so then phi would be the only unknown here. So let's use that. So 3, my z value, equals 5 times the cosine of phi. Okay, and I'm just using this. Okay. But then that, of course, divide by 5 here, so this is 3/5 equals the cosine of phi. And so then I can just take the inverse cosine of 3/5 to get my phi. All right, so I know that angle now. And by the way, the inverse cosine of 3/5 in radians is about, oh, I must be in degree mode, 0.93. Now, something that's important to note about phi is that you will only ever get values between 0 and pi for phi. So that's a requirement. So if I go back to our previous page here, some things that I should have noted from the outset is that you always want rho to be greater than or equal to 0. And that makes sense because, you know, it's a distance, right? So, so you're going to let that be greater than or equal to 0. Theta, you can let that be anything. We're going to allow for it to, you know, theta to be like even negative numbers, like negative pi or something like that. That just means you take off in the other direction if you go negative. And you can go tons of times around the circle, so it's not going to bother us if we do something like 20 pi. But phi, we're going to put restrictions on. Phi, we just want to be from 0 all the way down until you hit the negative z-axis, which would be at pi, right? So this is always between 0 and pi. I don't want to keep going past the negative z because I could have gotten there by just rotating through theta differently and then letting phi still be between 0 and pi. So we're going to put that restriction on it. So now let's find theta. Well, with theta, we can just use the same principle that we used with polar because theta is the same angle as in polar. So I can just say that the tangent of theta is equal to y over x. That's no problem. So this is going to be tangent of theta is equal to negative 2 roots of 3 over 2. So tangent of theta is negative square root of 3 over 1. But then that should be making us think about special values. So negative square root of 3 over 2 over 1/2. Okay, and so what theta is that? Well, we got to think about the quadrant this x and y are in. So y is negative, x is positive. So that means that we are in quadrant 4. So let's think about in quadrant 4. In quadrant 4 here, when is the sine negative root 3 over 2 and the cosine 1/2? Well, that would be down here at 5 pi over 3. So we get theta is 5 pi over 3. So my polar coordinates would be 5 pi over 3, and then the cosine inverse of 3/5 to keep it exact. So with these spherical coordinates, let's go ahead and try to get a sense of how we can convert equations into spherical coordinates. Now in example 7, we have that equation there in rectangular coordinates to start with. And I think this would be a good one where it would be good to know what this looks like ahead of time. So one of the things you might remember from just last section, in fact, is that when you have something of the form z squared equals x squared plus y squared, that's a cone. To put it into a 3D grapher, right, just take the square root of both sides, but then do both plus and minus, right, for the 3D grapher. All right, so let's go take a look at that. So with our cone, just go back to regular square root of 3 times x squared plus y squared. Then we'll make another one, and we'll just stick a negative in front. And of course, why does that look so bad? It looks so bad because of our discretization. So let's make that better, right? More pixels. So there we go. You can imagine we got a couple of cones there. So very good. So what would it mean to have a cone in spherical coordinates? So, you know, think about what kind of instructions do you need to give? Well, if you think about it, the only thing you really need to tell me is what phi is. Because if it's a cone, I know that all values of theta are going to be represented. And they are equal, or excuse me, for all values of theta are represented, all values of rho are represented, so I can go as far away from the origin as I want. Okay, but what's the thing that has to be constant about this? The thing that has to be constant is you only want a very specific phi value, right? So imagine the z-axis going straight up through here. You want to go at an angle from that z-axis until you hit here, and then you know that phi is equal to a certain thing for all values of theta and all values of rho. So that's what I kind of hope to work toward here, is instructions about what theta ought to be, or excuse me, what phi ought to be. Sorry, I'm getting tongue-tied here. So how do I do this? Well, let's use the formulas from the previous page. So I know that z is rho cosine phi, and we're squaring that. And then x is rho sine phi cosine theta. That's your x. And then y is rho sine phi sine theta. Okay, so let's see what that gives us. Rho squared cosine squared phi. And then I've got 3 rho squared sine squared phi cosine squared theta. And you're looking at this and thinking, man, this is going to be really complicated. Okay, however, some nice stuff does happen. Notice that we've got a rho squared sine squared phi in both of these. So rho squared cosine squared phi. And then I factor out a rho squared sine squared phi on the right side. And I'm left with cosine squared theta plus sine squared theta. And this is our best friend in trigonometry, right? When we see that every time, we know that that's just 1. So I'm left then just with these two things. But you know what? I can move these to one side. Right? You always want to be careful about dividing by variables, but I can move them to one side and say that that's equal to 0. But then that's powerful because I can factor things out. I can factor out my rho squared. So I have cosine squared phi minus 3 sine squared phi. Now, either this has to be 0 or this has to be 0 in order for this equation to be true. But let's understand that rho squared being equal to 0 is boring, right? Because that just means you're just at the origin the whole time. So we know that the real meat of this equation is here when these things are equal to 0. So that means that then cosine squared phi must equal 3 sine squared phi. And then if I do a little more manipulation, I divide by cosine squared and divide by 3 on both sides. I get 3 equals the tangent squared of phi. Or tangent of phi equals plus or minus the square root of 1/3, or 1 over root 3. Now, let's look at this. When will the tangent equal plus or minus 1 over root 3? Okay, well, that's going to be when the cosine is root 3 over 2 and the sine is 1/2. So that happens here at pi over 6. But then it also happens over here at 5 pi over 6, right? So keeping in mind that phi is always between 0 and pi, these are going to be the only angles we're going to include. So yes, there's values down here in the, on the unit circle that would give you positive 1 over root 3 or negative 1 over root 3, but phi is always between 0 and pi. So what that means is, I've kind of run out of room here, but the answer to our question of writing it in spherical coordinates is just phi equals pi over 6 and phi equals 5 pi over 6. This is kind of the upper cone and this is the lower cone. So just like we suspected when spherical coordinates, all that we really need to do is just identify the phi, and then rho and theta can be whatever they want. And so again, let's just go back to our picture right here. There we go. So there, if you go pi over 6 from from the positive z-axis, you get this, and then if you go 5 pi over 6, you get that. And you might say, boy, that angle doesn't look like pi over 6 and 5 pi over 6. Remember that if you have things on automatic, the z does whatever it wants. So if I adjust the z's so they're all the same, now look at that. Now from the z to here looks like pi over 6, and from the z down to here it does look like an angle of 5 pi over 6. All right, so last example here, and I kind of ran right into it, so maybe I should rewrite it. So we want to describe the solid where rho is always 1 and phi is between pi over 3 and 2 pi over 3. So what might be helpful here is to just think things in 2 dimensions for a moment. So if I think of things like in terms of, let's just say, the xz plane, so we'll call this x and we'll call this z, then, remember phi is measured from z, so we're talking about pi over 3 from the z-axis, right? So it's pi over 3 right here. So that puts me about at an angle of that, and then I'm going to go out until my rho is 1. Okay? And then I'm going to go 2 pi over 3, so that's going to maybe put me down here, right? So 2 pi over 3, but throughout all of that, rho should still be 1. And so about the same there. And so what we've got is something like this. But understand that this is just a little cross section in the xz plane, and of course theta can be whatever it wants, right? So I'm going to have the exact same thing over here, right? Exact same thing. because theta can whip around and be over there as well. And so what's going to happen here is that as I give this some three-dimensionality, it's going to come out at me and it's going to circle around. So what I've got is a portion of a sphere. It is really what we've got here. So, I could try to, do something like this. So this is what we're dealing with, is kind of a portion of a sphere of radius 1, where we're only getting the part of it that has angles of phi that are between pi over 3 and 2 pi over 3.